Okay, so welcome to lecture number 8 on Math 140 SCI. This is September 23rd, and we're going to start by doing an example from section 4.5. So I'm going to share my screen here. Take out your calculator, you're going to need it. And got it. Okay. Okay, so question 4.5. Okay, so there's a question 4.11 in the book. It says brain size and intelligence. Brain size and intelligence. For centuries, people have associated intelligence with brain size. A recent study used magnetic resonance imaging, MRIs, to measure the brain sizes of several individuals. The IQs and brain sizes of 6 individuals are as follows. So we have the brain size versus the IQ of 6 individuals. We have 100, 140, 90, 90, 95, 100, 92, 135, 88, 80, and 106, 103. A, make a scatter plot. So someone remind me from last time, how do I go ahead and make a scatter plot? And before you answer that, before you actually do anything, because I want to make sure you have your explanatory and response variable correct, which is the explanatory variable and which is the response variable? Which one explains the other?
Does the size explain the IQ?
Well, that certainly seems to be the more likely scenario. So yes, the size will be the explanatory. And Cynthia, I saw you wrote it as well. And the response should be the IQ. Right? It's not like you have an IQ and then your brain changes accordingly. But your brain will evolve to a certain size, and that might affect the IQ. Seems much more reasonable. So how do I go ahead and create a scatter plot? What do I do?
You click stat first.
Let's click stat. Then
Edit.
click edit. And then
You type in size for L1 and then IQ for L2.
okay, size for L1, IQ for L2. Next. Next. Wow, we did it 2 days ago, right?
You do second and then stat plot.
Okay. To make sure what?
I don't remember.
Plot
The stat
one.
plot. The stat plot you only have to do once to make sure your stat plot is on. If it's on from last time, you don't have to do it again. But what should you do at this point?
Don't you click second quit?
Yeah, and then
and then click stat again.
Not to make your scatter plot. That's to calculate your correlation.
You adjust the window.
Adjust the window. So what is a good min X and max X value for this example?
Wait,
Yeah.
we do click second and then quit?
Well, second quit takes you back to the main screen.
Oh, okay.
And so anytime you're at a place that you don't like to be at, you can always do that.
So where do we go from?
Well, we want to graph it, but we want to make sure that the window will show me all my points. So we
But from here, I
adjust-
click graph, right? Just,
No, not yet. Not till you adjust your window first.
yeah, but how do I get to the window part?
Well, there's a button that says window on the very top of your calculator.
Right, okay, thank you.
If I don't hit the button that says window. And what is a good lower X and upper X for this particular problem? What's a good lower X and upper X for this problem?
0 be for lower X.
Well, what's the smallest X value? So the
88.
small- 88. So I chose 80. 85 works, 80 works, 70 works. You don't want to go too far away because then all your points are really bunched up. You want to be able to see what's going on. So I think I did 80 to 110. That's what I did for my X's. And what's a good range for Y's? $75, that's a good lower. What's a good upper for the Ys? 150, that's pretty good. I personally chose 70 to 150, but nothing wrong with 75. Maybe it's even better.
Professor.
Yeah.
On the top of mine, it says shade res. What do I
Okay.
do?
Wait, on top of what? Where are you right now?
On window, it says shade res, X min, X max, and then it says SCL, and then
Okay.
it says Y min, Y max, and then Y SCL.
Yeah, so it's the X min and the X max and the Y min and the Y max that you're adjusting.
Okay.
You want the X's to be in the range where you see all your points, and you want the Y's to be in the range where you see all the points. Once you hit all of those, then you can hit graph.
So what do I put for shade res and
Um,
the XSCL?
Mine are all ones.
Okay, and then shade res, keep it as a 1, 2.
I don't have that button on mine. Distance between tick mark. Okay, oh, it says it what it is. I don't.
I'm pretty sure you can just leave them blank because mine are blank.
Oh, okay, good. Yeah, mine, I don't have those buttons. Well, now you can hit, now you can just hit graph. Once you set your window, just go ahead and graph it.
Do I keep the XSCL as blank as well or 1?
Mine is one.
Okay.
So this is what mine looks like. Is that what yours looks like roughly? Again, if you have different bounds, it's going to look a little different or very different depending on what your bounds are. So the scatter plot. I don't know, mine looks something like that. Not perfect, but something like that. Part B. Find the correlation coefficient. It has to do with step by step, but we have a calculator, so let's just use a calculator. How do I find it on the calculator?
Hit stat.
stat,
and then enter,
enter,
edit,
edit.
and you put in the data points for list 1 and 2.
Oh, we already had them from before, don't we?
Oh, so then don't you just hit stat and then you go to calculate?
Yeah, but which calculate button is it going to be? Calculate has a row of possibilities.
The R.
You see an R there?
Is it the fourth one?
Then reg AX plus B. Yeah, then two variable. Well, not two variable, it's the lin reg AX plus B. What R do we get? What R do we get? Right. 0.377, which tells us what about a correlation between, by the way, what's my R squared value? It is positive, which is true. But how positive is it?
It's weak.
Very weak. Very weak. So weak that I might not even recognize that it's linear at all. Now, it doesn't mean that there's not a different pattern. Maybe I'm not seeing it. I only have a small sample size, only 6. Right? If I really wanted to study this, I'd have hundreds, if not thousands of data points. With 6, I mean, you really can't conclude anything with 6. This is just an exercise, excuse me, this is an exercise to use your calculator to get the values. I would never statistically make any conclusions from the sample size of 6. But it does show you how to use it though. Does that make sense? Questions on this? Okay. So what I want to do today is chapter 5. Now, I already did a significant portion of chapter 5 last time, at least in terms of using your calculator to get an answer. So chapter 5 is on regression. And regression is once you recognize that there's some kind of pattern of your data, whether it's linear or nonlinear, but once you recognize that there's a pattern, the next step is to say, okay, I think it's linear. My R value is pretty high. Suppose my scatter plot looks like this. Okay, would I conclude based upon this data that my relationship is linear or might be linear? Does the data seem to indicate linearity here?
Yes.
Sure, right? So the next question is, if it's linear, then what is the true line that is really being represented by my imperfect world data? In an imperfect world, nothing's ever going to land exactly on a straight line. There's imperfections in the world. There are things that I'm not considering that are factors. Like, for example, if we do the age versus height example from last time, then we know that as young adults, as children get older, that their height goes up, correct? Does everyone's height increase at the same rates? Are two people of the same age always going to be the same height? No, so there's other factors that I'm not considering besides just age and height. What are some other factors that might play a role in why one person wouldn't be the same height as another?
Gender.
Well, go on. Genetics. I heard that one. Anything else?
Diet?
Diet. She says as I eat bad food. Okay, I get it. Very passive aggressive, but I get it. All right, what else? Yeah, I work all day. I gotta get my meals in when I can. So I don't know. Maybe there's other things. That's the whole point. You never really know if you're considering everything. When I just look at age versus height, there are factors that I'm not considering. So how active a person is. We'll just say active, sure. Okay, I don't know. I used to weightlift when I was in high school. And people used to say, oh, that's gonna stunt your growth. I don't know, does it? I don't know. I'm not a doctor. Maybe it does, maybe it does not. Who knows? Perhaps there are things that you can do that will affect your height. I don't know. The point is that there's certainly going to be factors that we consider, and there's certainly going to be factors that we don't consider. So question for you. What percent of the response variables variation is explained by only the explanatory variable? This is a big question in stats, which is a very simple answer, by the way. What percent of the response variable's variation is explained by only considering the explanatory variable? In other words, in the case of height, yeah, different ages are going to give different heights. But then there are other things that also explain why I might have different heights. So what percent of the variation in height can be explained by only considering the explanatory variable? The answer, can anyone guess? And this would really be a shot in the dark if you've never seen it before. But can anyone just straight up guess something that we've learned so far in this course as the answer to the percent of the response variable's variation that can be explained by the explanatory variable and not the other factors? Can anyone take a guess? Again, I don't expect any logic behind your guess because it would solely be a guess. 50.
0.
0. So you're saying, one second, let's go both those answers. What I'm talking about is every scenario across the board, whether it's the age, height, or every other example in the universe, the claim is either 50% can be explained by the explanatory variable or even 100% or 0%. Well,
100%.
again, I'm not looking for a number here, guys, because it's different in every example. Sometimes the explanatory variable explains 100%. Sometimes it explains 0%. If I say, I'm going to measure height of individual versus who won the Super Bowl last year or the year that they were born. Okay, that's it. I'm going to look at who, well, that's not quantitative. It's got to be quantitative. Okay, so how about this one? Amounts of rainfall on the day that you were born to explain how tall you are when you are 8 years old. How much of the reason why people's heights vary when they're 8 should be explained by how much it rained the day that they were born? That should be 0, right? That should have no effect on their height. But if I said, I want to measure how much water is in a cup that I left overnight, and my explanatory variable is how much it rained that night, I would expect a very high connection between them, right? Sometimes the explanatory variable is like, this is everything. I don't need anything else. Sometimes this has got nothing to do with it. This is 0%. And sometimes it's somewhere in between. So I'm not looking for a number. I'm looking for some kind of variable that we've come across in this course. And the answer is no problem. The answer is R squared. That number that we calculated last time, the R squared value. The R squared value is the percent of the response variable's variation that can be explained by only the explanatory variable. If I have an R squared value, like in this example here, of 0.142, what that means is 14% of the variability in IQ comes from brain size. Where does the rest come from? I don't know, but it ain't brain size.
Any other variables?
Anything else out there that I just am not considering in this particular experiment? Now, if someone told you that, if you say, I think brain size really affects IQ, and you say, well, I ran the data and only 14% of the reasons why people's IQs differ is because of brain size, would you be agreeing with that person or would you be disagreeing with that person? To answer that, you had to follow that whole argument. If not, if you lost me halfway through, it's gonna be a hard time to answer that one.
Great.
So again, if someone comes to you and says, I think brain size really affects IQ, I would say, I disagree with that. Because according to my numbers, only 14% of the reason why IQs differ across people can be attributed to brain size. 14%. That's next to nothing. 85% will be other stuff. So the R squared value, now we can get a better appreciation for why the R squared value is what we use when it comes to the strength of the correlation. Because what we're really measuring is what percent of the variability in your response variable can be attributed to your explanatory variable. If it's like 85%, 90%, that's a lot. That's a very strong correlation. If it's 15%, 20%, 30%, 40%, that's very weak. And somewhere in the middle will be moderate. Does that make sense? Yes, no, maybe so? All right. However, while that's all important, that's actually a little bit later in the chapter. What the chapter starts out as is once you've determined that the relationship should be linear, the next question you want to ask yourself is, what is the real line underneath the data? Would this be the line that the data is truly representing? It's clearly not. How about this? Would that be the line? Clearly not. What about this? Could that be the line? Well, how do I know it's that and not something like this, which is like slightly different, minusculely different, although that was amazingly like almost exactly the same. Let's say I do that instead. Which of those lines is better? You can't tell just by looking which is better, unless you were going to try to, in which case I apologize for basically setting you up for failure. That wasn't where I was going with that. But you cannot tell by looking which of those lines is better. However, not all is lost, because we have a mathematical way of determining what the best fit line is. And do you guys know who came up with the best fit line? in the 1800s? Anyone know who it was? Anyone know their mathematicians throughout history? Anyone know any math guys? Albert Einstein, good guess, but no, he wasn't born yet. That was he was born in 1877, I think. No, 77? 18.
I just looked it up.
That's cheating. But what do you got? Is
Is
it
it-
is it KFG?
Oh no.
Doesn't his initials are not KFG?
No.
Oh, well, who are you looking at?
I don't think this is right.
Well, what does it say? What does it say?
Richard Thane? That is not right.
Well, sometimes we discover things years later that someone discovered something and nobody knew about it. Like they find some manuscript in some library in the middle of nowhere and they look through and they realize, oh my God, this guy discovered it 100 years before we ever knew. So maybe what I'm thinking is not correct. I don't know that guy. So that's not the one that I'm thinking of. It was not Newton. Newton was in the 1700s. His name was Carl Friedrich Gauss. Did anyone ever hear of young Gauss, the greatest mathematician of all time? No? I want you to imagine the following scenario. Imagine the following scenario. Everyone, listen up to this one. Your first day of school, you're 8 years old. Okay, you've never been to school before because you lived in the 1800s. It's not like us, we go to kindergarten and first grade and so on. This is in the early 1800s. You're 8 years old, the first day of school, and the teacher is getting a little frustrated with the students not really working hard. So he gives them the following problem. He says, you know, kids, students, young people, I want you to add up every number from 1 to 100. And the teacher says to himself, haha, I got them. This will take them hours. They don't have calculators. They have little slate boards. They write 2 words, they got to erase. They write 2 more words, they got to erase. This will take them all day. I am golden. And it's your first day of school. You're young Carl Gauss. And in a second, you say, oh, that's just 5,050. The teacher says, how do you get that? And you say, oh, well, it's quite simple. I didn't add them in order. I first added 1 in 100. What do you get when you add 1 in 100? This should not be tough. Gauss got it. You should be able to get it. What do you get when you get 100? And what's 2 in 99?
101.
And what's 3 in 98?
101.
All the way to 50 and 51. What's that?
101.
Oh, so that just means you have 50 copies of 101. Now, is that really that impressive? Not really. But when you're 8 years old and you've never done math before in your entire life, and your first day of school, you're given that problem. I don't know. That's pretty nice. So that was young Carl Gauss. The story might be apocryphal. Nobody can verify it, but they don't tell stories like that about you and me. I'll tell you that much. Right? So Gauss is the one who I've always learned was the one who came up with the best fit line. So how do we find the best fit line? So here's what we do, or here's what he did. We don't have to do it because it requires calculus and it requires, calculus to derive the formula. And so we're not going to worry about that. We're just going to use our calculators to do it. But suppose you have, for the sake of discussion, you have 3 plot points. You have 3 data points. And your goal is to find the best fit line. So you take a guess and you say, I believe that the best fit line is this. Okay, that's your guess. So this is what Gauss said to do. He said, okay, notice that all of your points don't exactly fall on your line. Maybe coincidentally, some of them might, but for the most part, they don't. He said, calculate how far off the line vertically each of your points is. Okay, those he called the deviations, how much each point deviated from the line. He said, calculate all your deviations. You have deviation 1, you have deviation 2, and in our case, you have deviation 3. He said, take your deviations, square them, and add it all together. And you get a number. Now, if someone else came along and said, I don't think that's it, I think this is the best fit line. So this will say is someone else's guess. Then Gauss says, no problem. You think that's the best one? Calculate your deviations. That's your first one. That's your second one. That's your third one. We'll call this D1 prime, D2 prime, and D3 prime. He said, square those and add them all together. By comparing these two numbers, we'll call them A and B. By comparing these two numbers, what would you do if you look at your numbers A and B? How would you decide which of those two lines is the better best fit line?
The one that has the smallest deviation.
The smallest total, right? The smallest total. So what Gauss said is, do this for every one of the infinitely many possible lines that can exist in the universe, and take the one that gives the smallest value of what he called the sum of squares, the sum of the square deviations. Whichever line of those infinitely many lines gives you the smallest value of the sum of squares, that's your best fit line. So if someone says, no, I think it's this, you say, no problem. Let me take my deviations, let me square them, let me add them together. And is my number smaller than yours? If it is, mine is better. If yours is smaller, then yours is better. The smallest, that's the best fit line. Now you might say, how exactly do you examine every one of the infinitely many lines possible to decide what the best one is? So luckily, with the rules of calculus, you don't have to. With calculus, you can actually come up with a formula that will find the best one for you without having to actually manually go through any of them. So people hear the word calculus and they say, oh my God, it sounds so difficult. I had a friend who took it in school and they wanted to kill themselves and it was horrible. I know calculus. But it turns out with calculus, you can do some really amazing things. This just being one of them. So if that doesn't convince you to become a math major, I really don't know what will, because I mean, that's like, wow, you can do that with math. It's amazing. And I'm not really getting any, jumping for joy pictures or anything like that. So we're just going to assume that you all think I'm crazy and just go forward. So the point is that the way to find the best fit line, so the best fit line or the least squares line is by minimizing the sum of the deviations squared. You take each deviation, you square it, you add them all together, you minimize that. And that's the best fit line. And we already showed how to find this on a calculator. Let's do it for the example that we did before. If you go back to your last picture, if you're still there, after doing the stat, calc, lin, reg, if you're still there, then you'll notice that you already have your best fit line. It comes along for the ride. Because the very first line is y equals ax plus b. Right? Ax plus b, that's a line, right? Mx plus b usually we use, but ax plus b, same thing, correct? All we need is a and b. Well, they give me a and b. They're right there. In fact, let's write that down. So example from above. A equals 1.355 approximately. B equals negative 20.9. And y equals ax plus b. So what I want you to do is I want you to graph this line. How do I graph this line?
You go to y equals and
Y equals,
equation with the x.
put in for y equals ax plus b. And then hit graph again. And you should see this. Everyone get that? Yeah? No?
Where do I go after I entered all the data in Y1?
Oh, are you, wait, you mean list one?
Yeah, when I enter 1.355x plus negative 20.9.
Oh, just hit the graph button.
Okay.
Did you get what I got?
Yes.
All right, we all got this? Okay. Any questions on that? Now, because it might show up on a test, you should know what the least squares line formula is. What is the formula for the least squares line? We know it's y equals ax plus b. And we want formulas for a and b. So first A is the following. So what is A? Someone read it to me, please. Don't just read the letters, but tell me what A is. So for every symbol, explain what it is. Don't just read it to me. What is A?
Slope.
Yes, but in terms of what I wrote there on the board, what are the three
Correlation.
factors? Correlation? What else do you need besides correlation? There's two other factors there.
The standard deviation from y to x.
Yeah. So what's the difference between SY and SX? What's SY and what's SX? So they're both standard deviations. SY is the standard deviation of the Y values. And SX is the standard deviation of the X values. And B is equal to that. And just a formula for those deviations that we spoke about before, also called residuals, there's another name for it, is equal to the observed minus the predicted. And I want to use an example of that so we can see how to actually calculate them. Oh, this is a good one here. So after you write that down, we'll go ahead and we'll do an example. By the way, before we do the example, what's the formula for B there? What are all the terms that fall in the B formula?
The mean of the y value minus a, which would it be r standard deviation of y over standard deviation x
Right?
times the mean of the x value.
Wonderful.
Value.
Wonderful. So let's go ahead in the last example. And so still that same example from before, so we still have it in our calculator. Let's find x bar, sx, y bar, and sy. How do I find those all? With the same example from before. All in your calculator. But how do I go ahead and find all those values?
You have to look at the data for the X and Y values of the problem and find the mean.
Great. Tell me how to use your calculator to get them. I don't do it by hand. I want to use my calculator. So how does my calculator get them for me?
Do you use the two variable statistics?
Two variable statistics is a good guess. And actually, it's a great guess because there they all are. So yes, that's wonderful. All right, so two var stats. What do we get for x bar?
$95.166.
95.166 is forever, so we'll say 6 bar. What's SX?
6.77.
Okay, awesome, 6.77. What's Y bar?
108.
108. And what is SY?
24.29.
Oh, let's do a 24.3. And in fact, for X bar, we'll do 95.2. Just to keep, 3 sig figs across the board. So your calculator can not only compute R directly, and it can't in the best fit line directly, but it can also give you the individual values from which you can compute the best fit line. Of course, why go halfway? If you have your calculator to get you the final answer, just get the final answer, right? Right? So if I now go back to that problem and I copy this. Okay, so we know the best fit line was y equals 1.355x minus 20.9. correct?
Yes.
Okay. So what is my first deviation equal to? What is my first deviation?
Four 4.8.
How do you know that?
I did
I'm not saying you're wrong. I just want to know how you know that.
I did 100 minus 95.2.
I see. I see. Okay, okay. I see what you're doing. All right. So that's not the deviation for this type of problem. But I know exactly what you're doing. You're doing what we did earlier in the course, which was each x value minus the mean, 100%. In this example, back in this picture here, I'm looking for that. I'm looking for the distance, the deviation, the distance of the y value of the actual points and the y value of the predicted points. In other words, this is what I actually got, right? This is my observed data point, right? That's my observed. If the red line was truly the correct line, then this is my predicted value. It's on the line for the same x value. So the deviation is what I actually got minus what the line predicts that I would get. So if I look at my data, what was my first y value?
140.
140. Minus, what is my first predicted y value? Now I don't have this number, but how do I compute that predicted y value for the first point?
You plug in 100 into the formula, the least squared
Perfect.
best fit line. Yeah.
100, 1.355 times 100 minus 20.9. Because 100 is the first x value. So if I plug 100 into the formula, it will give me my predicted y value, which is how much?
$114.6.
114.6. And 140 minus 114.6 is a deviation of 25.4. So the first deviation is 25.4. Each point has some deviation. If I add up the squares of all the deviations, whatever number I get is as small as it will ever get if I imagine every possible line in existence. Does that make sense? Notice, by the way, for this example, if you look at your graph again, which of these dots on the graph corresponds to the first point that I just solved for? Which dot corresponds to the first point? There's how many points there on this graph? There's 1, 2, 3, 4, 5, 6, correct? Which of those dots is the first points on my list? Is that one? The one that I just computed the deviation for. Which of those 6 dots is that one?
Is it the second to last one?
Well, to be a little better, I have 4 in the bottom, left to right, 1, 2, 3, 4, and then I have 2 on top, left and right. So which of those 6 is the first point? Top or bottom, and whichever it is, which of those numbers? 1, 2, 3, 4, or 1 or 2?
Top 2.
Top 2, I agree. Because if you move your cursor over there, notice that my cursor is blinking on it. And what does the bottom say for my X and my Y? X equals what? Y equals what?
X equals 100, Y equals 140.
X equals 100, Y equals, well, approximately 140, but certainly that's the correct dot. Agreed? Notice that that dot is above the line, which means that my deviation for that dot is going to be positive because my observed is greater than my predicted. So observed minus predicted is positive. The dots that are beneath it, my deviations are all going to be negative because the observed is lower than the predicted, correct? Now, if I just add up my deviations, some are positive, some are negative, I'm going to have cancellation. In fact, you can actually mathematically prove that if you add up the deviations for every example, no matter what line you pick, you will always get the same total answer, which is 0. The deviations will always add to 0. But if you square the deviations, then you create only positive numbers, or at least non-negative numbers, and you don't have that same cancellation effect. Does that make sense? Now, do me a favor. Move your cursor on your diagram. I would like you to move your cursor to X bar, Y bar. Move your cursor to X bar, Y bar. What is X bar again? I forgot.
95.2,
And what's Y bar?
108.
So move your cursor to 95.2, comma, 108. What do you notice?
It's in the middle.
It's more than just on the middle. That might be the middle of your window, but it's more than just that. Where is X bar, Y bar?
It's on the line.
It's on the line. X bar, Y bar is always on the best fit line. Always. Are we all with me so far? Any questions? Okay, only a couple more things that I want to cover today. So the first one is on what is called a residual plot. A residual plot is a scatter plot of the residuals, or what we're calling the deviations, versus the explanatory variable. In other words, you have your original scatter plot, right? You have your original scatter plot. And then what you go ahead and do is you calculate your residuals for each of your data points. And then you make a new scatter plot where the residuals become your new Y values. So rather than plotting your original Y values, you change them, you throw them out, and you plot just the residuals. What you get then is called a residual plot. And residual plots help us assess various more sophisticated ideas. But most importantly for this level, it helps us determine whether or not the regression line fits the data. Okay. Residuals, there's a whole section on it here on page 138. There's some, well, let me show you. Let me load up the screen here. Hold on. So ebook. And we are in 5.5 residuals. Okay, so let me share my screen. Okay, so so here we have residual plots. Okay, so here are 3 residual plots. Okay, if you really believe that the best fit line fits your data well, then what we're looking for is a residual plot like the first one. What you'll notice about the first one is that the spread of the residuals is pretty much constant throughout the entire range of values. Unlike the third one, where the residuals are very, very small and then get more spread out as you go down the line. So the one thing you want is you want constant variation of residuals across the entire range. And you also don't want something like the second one, which is a pattern of residuals, where they're negative, positive, and then negative. That would indicate that it's not linear data. You don't want patterns, and you want constant variation of residuals across the entire range. Those are the 2 main things that you're looking for, either one of which would lead you to conclude that it's not linear and you should not use the best fit line in a predictive way. Okay, does that make sense? Again, I'm not really going into the details of why this is the case. I'm just giving them to you as facts, because a lot of the things in statistics, you really need more sophisticated techniques to fully understand, which is why stats can oftentimes be difficult for some students, because you want explanations so that you have a deeper understanding, but you can't be provided with those explanations because the reasoning behind them is just too sophisticated for the level. Okay, this is not like trigonometry or calculus or most regular math classes where I can explain pretty much everything at any time because you have everything you need to understand that which you're learning. In statistics, unfortunately, I just can't do that. So again, for residual plots, 2 things: constant variation and no patterns of residuals are the 2 things you need to determine that the regression line fits the data well. Okay, does that make sense? Questions on that? Yes, no, maybe so? All right. Since I have this up anyways, I'll just continue to use it. The next concept is that of an influential observation. If you have an influential observation, it means that if I removed it, my calculations would change significantly. If I have a mean, if I have a slope, if my best fit line has a slope of 5, and then I remove one observation and it becomes -3, I'm going from positive correlation to negative correlation, right? That one data point was influential. It had a huge influence on my results. Outliers in general are influential. Okay? Yes, no, maybe so? So in the box here, very important result in the box. Okay? if there's influential observations, then the results of your calculations may be of little practical use. If there's influential observations, then chances are you can't really apply it in a more general or even in the specific case. There's too much going on that is not ideal for analysis. But more specifically, if you have outliers in either the X or Y direction, they are often influential specifically for the correlation. And outliers in the X direction are often influential for the best line itself, which of course is, you need the correlation to get it, because remember, your slope was R SY over SX. So you need the R in there, but this is a general result. Either the X or Y direction will affect the correlation, and in the X direction will affect usually the least squares line. Okay. So like, here's an example. If you look at this scatter plot here, you have subject 1, which is an outlier in the X direction, right? It's way out here off to the right. But if you removed it, they're telling me that my new best fit line is pretty much the same. It's not really influential for the best fit line itself. Does that make sense? Okay. Now here, if I remove subject 2, which by the way is an outlier both in the X direction and in the Y direction, then it had a humongous effect on my best fit line. Right? It used to have a positive slope because that one guy up there was really lifting it up. And then we remove it and it dips to a negative slope. So here, subject 2, it would be an influential observation. How do you determine if it's influential or not? Well, you got to redo your data every time you remove something. Remove it, recalculate. Oh, it didn't change much, not influential. Remove it, recalculate. Oh, it changed a lot, influential. So you can't really do it by eye because you can't really make best fit lines by eye. Does that seem reasonable? Yes, no? Everyone else? Anyone? Okay. And then finally, last section, a few cautions when computing best fit lines, correlation, regression, all of this stuff. Again, as I mentioned before, they're only for linear relationships. Only linear. Okay, if it's not linear, they can be really correlated, but my math will not tell me. So do not try to do it for non-linear relationships. Also, correlation and least squares regressions are not resistant. An observation, an influential observation, can have a huge effect. One outlier can have a huge effect on either correlation or regression. They are non-resistant. So always be on the lookout for them. I really wouldn't worry about this too much. I've never seen this asked on a test ever. And usually I don't get too much into it, but I would be remiss if I didn't at least mention it. If you base your correlation on averages rather than in the individuals, it can often be very well, misleading. Oh, that's what they say here. It can be misleading. Okay. Always go to the individuals, never to averages. So I'm not going to say something like, okay, let's take the average household income for the 50 United States. That is 50 data points, but it's data points based upon averages versus going to the individual households themselves, which are the individuals. And the last one is extrapolation. This is a big one. This one I do ask on. and usually people get it wrong. Do not make predictions outside the range of your data points. Imagine, for example, that you are comparing age versus height for children from when they were born to when they were 3 years old. And you see this nice linear upward slope that as they get older, they also get taller. And then I say, okay, how old will a 40-year-old be? And you say, oh, no problem. Let me just get my slope and do my best fit line. Oh, he's 9,000 feet tall. Because that's what my data gave me. I'm taking my data, which applies to people from born to 3 years old, and then trying to use it for someone who's way outside of the data at 40. That's called extrapolation. Don't do it. I'm not saying it's never correct to do it, but it's almost always incorrect to assume that it works without actually checking the specific scenario. And the last one, I mentioned this before, a lurking variable. Just because two variables are correlated does not mean that one causes the other. Correlation does not imply causation. There can always be some variable lurking behind the scenes that explains why two variables are connected. Does that make sense? Any questions on anything we covered today? The first test will be on those 5 chapters. The first test, let's look up when it is. Let's remind ourselves. How do I, okay, here. October 5th, I think it was that what it was?
Will it be on Achieve?
I'm sorry?
Will it be on Achieve?
It will be on Achieve. The comprehensive quiz on Achieve. It's currently hidden. Let's see what it has. It says when I click on it, it's due Monday, October 4th. You will have 70 minutes to do it. Let me check the let me check the syllabus to see whether or not it is an in-class thing or not. October 4th. Yeah, here we go. So it says Thursday, September 30th. That's a week from today. A week from today will be the quiz. The comprehensive quiz on chapters 1 through 5. 9:30. It's on the syllabus. It's not a surprise. I might not have remembered that, but it has been on the syllabus the entire time. So a week from today in class, next Thursday, will be the comprehensive quiz on chapters 1 through 5.
Did you say that was like on campus or?
No, it's not on campus. It's on the on Canvas. The syllabus on Canvas says that it is September 30th. Chapter 5, comprehensive quiz, 70 minutes, chapters 1 through 5.
So it's we log on at 4 p.m. on Zoom.
Log on at 4 p.m. Now, I am flying out Thursday nights, but I had planned on being in class and then going to the airport afterwards. I might get a sub because it's only an exam and the sub would just be here. I don't even know if you have to be on camera for it. So I don't even know if that will be required. Maybe as I drive to the airport, I'll hotspot from my car and I'll log in as I drive in the seat next to it. Actually, that's probably the best idea. Let's do that. That way I don't got to get a sub and I can not have to worry about it. But Thursday, next week, 4, and you'll have 70 minutes. I have no control over that. So 4 o'clock until 5:10 will be the comprehensive quiz. A week from today. Now, when I look at the due dates and whatnot for the various achieve dates, the chapter 4 is due 6 days from today, September 29th. Chapter 5 is not due till October 4th, but I highly recommend, how many questions? It's a good question. I just was looking at that. It's, let's see, 24 questions. 24 questions. I see some on 1, I see some on 2, I see some on 3, I see some on 4, I see some on 5. So it looks like it's 24 questions, runs the gamut from 1 to 5. You'll have 70 minutes. That's roughly 3 minutes per question on average. Huh?
Quick question on the test or the quiz.
Yeah.
So even though chapter 5 isn't due till October, does that mean like in terms of the test, it is like there's going to be less questions on chapter 5, or is it going to be
No.
equal out?
No, it just means that while the official due date for 5 is October 4th, I highly recommend getting it done by September 30th, because that's the day of the test. So, yeah, get it done in a week. That would be my recommendation. But I can't tell you exactly how many questions are going to be from each chapter. But let's just say that there's some from each chapter. Okay. Now 4 and 5 really go together. Anything you use your calculator for 4 and 5, they're really connected. 1 was a lot of graphical stuff, box plots and pie charts and histograms. 2 was means and deviations and medians. 3 was the normal stuff. 4 was correlation. 5 was regression. So 5 basic topics. And your test will be a week from today. Sound good?
Yes.
Okay. Well, in that case, if there's no more questions,